430s. This video is on lesson 4 from the chapter Polynomial Functions and Equations. Before we get into the remainder theorem and the factor theorem, it goes through an example from lesson 3, which is using synthetic division to divide. So remember that when you're given a polynomial function, two things you want to make sure of. You want to make sure it's in descending order of x, and you want to make sure there's zeros as placeholders. So if I was to rewrite this polynomial function, it would be x cubed minus 2x squared plus 0x minus 4. So my 0 placeholder would be for the x. Then to synthetically divide, what you're going to do is set up your upside down division bar. And remember, the first row is going to be the coefficients of each term in your polynomial function. So that would be a 1, -2, 0, and -4. What you want to put in front of your upside down division bar is the root of the divisor. So this is my divisor here, x plus 1, and the root of the divisor would be -1. How you would find that out is if you just set your divisor equal to 0 and solve for x, you would have x is equal to -1. That's the root of the divisor that is going to go in front of the upside down division bar. Okay, for synthetic division, drop that first term and carry out your multiplication. With synthetic division, we add, unlike long division where we subtract. -2 plus -1 is -3. Carry out your multiplication. -3 times -1 is 3. Add, and you get 3. Multiply, you get -3, and add, and you will get -7. Remember that this last term here is always your remainder. So when we synthetically divide by this binomial, our remainder is going to be -7. This is our quotient, so that's our q of x. And if I was to rewrite this polynomial function as a division statement, what it would be p of x is equal to. So how I would get this original polynomial function is by taking my binomial, which is x plus 1, multiplying it by the quotient. And remember how to figure out what this quotient would be. If this is a third degree polynomial, your quotient would be a second degree. It's always 1 degree less. So that would be x squared minus 3x plus 3. And then you're going to add your remainder, which is plus -7. So I'm just going to write -7. That is your division statement. The second thing that it's saying is now it's asking us to calculate p of -1 in the polynomial function. So it's the exact same polynomial function, and they want us to calculate p of -1. Remember, this is saying when x is equal to -1. So take out your x, and they want us to calculate p of -1. Every single time you see an x, substitute it in for a -1. So -1 cubed minus 2, -1 squared minus 4. P of -1 is equal to -1 minus 2 minus 4. P of -1 is equal to -7. What they want you to see and to understand in this example is whether we are synthetically dividing by this root of -1, we get a remainder of -7. Or if I calculate the polynomial, inputting the root of -1, I get the exact same remainder. So whether you're using synthetic division or whether you're inputting the root into your polynomial, your remainder will be identical. What I want you to also understand from this is a point on your graph. So p of x is a polynomial function that we could input into our calculator. And on the graph, on the polynomial, when x is -1, the y value would be -7. Let's look at the remainder theorem. So what the remainder theorem states is as follows. If you have a binomial, so let's say the binomial is x minus a. If I said, what is the root of that binomial? You know that if you set it equal to 0, the root of the binomial is a. The remainder theorem states the following. If you take any polynomial and you input the root of the binomial, which would be a, the answer which would be your output, that is always going to be your remainder. And that was demonstrated in this first class example, right? We input the root, which was -1. The output was -7. That was our remainder, which we saw using synthetic division. So this is what the remainder theorem is. Let's look at class example number 1. It says use the remainder theorem to find the remainder when this polynomial function is divided by x plus 1, so this divisor, and then 2x minus 1. When it says use the remainder theorem, you are not using synthetic division. The remainder theorem is P of A is equal to your remainder. And A, remember, it's always the root of your divisor. So the root of this divisor would be -1. So if I input into my polynomial function a -1 every time I had an x, and I calculate that, the output would be the remainder. So 6, -1 cubed, minus 4, -1 squared, plus 8, -1 plus 6. P of -1 would equal -6 minus 4 minus 8 plus 6. P of -1 is equal to, if you calculate that, the answer would be -12. This answer is the remainder. So the question was saying use the remainder theorem to find the remainder. So the remainder is -12. And again, it's not asking this, but if I said on your graph, when x is -1, what's the corresponding y value is -12. For this one here, if your divisor is 2x minus 1, and I said what is the root of that binomial, you would add 1 to each side and divide by 2. The root of the binomial would be 1/2. So if I was to calculate P of 1/2, now I'm going to input a 1/2 every time I see an x. That would be 6 times 1/2 cubed minus 4 times 1/2 squared plus 8 times 1/2 plus 6. P of 1/2 is equal to, if you were doing this in class, it is enough to have this as your first step. You could then enter this onto your calculator and just write the output here. But what it would be if you were entering each term separately, it's going to be 3/4 minus 1 plus 4 plus 6. And then P of 1/2, when x is 0.5, the remainder is going to be 39/4. That is my remainder. So remainder is 39/4. Let's look at class example 2. It says find A, so we're missing a coefficient here. If the remainder is 131, when this polynomial function divides this divisor. And there's two ways that we could actually calculate this. The two ways are using synthetic division and the remainder theorem. Let's start by using synthetic division, and then we'll finish using the remainder theorem. So setting this up, you look at your polynomial function and make sure it's in descending order of x, and we have 0 as a placeholder. So we need to rewrite this because we need a 0 placeholder. So P of x is equal to 2x to the 4 minus, I'm going to put 1x cubed. The 0 placeholder would be for the x squared, so 0x squared minus ax plus 8. The root of my divisor is 3. The root of the divisor goes in front of the upside down division bar, and the coefficients of each term go in the first row. So those coefficients would be 2, -1, negative a, 2, negative 1, 0, negative a, and 8. And then don't forget, it tells us the remainder. So it says the remainder is 131. That would always go here, because this always gives us our remainder. Okay, let's carry out the synthetic division. We'll be able to calculate what our missing value of a is. Drop that first term, which is a 2. 2 times 3 is 6. After your addition, you're going to get a 5. 5 times 3 is 15. After your addition, you have 15. 15 times 3 is 45. And then after your addition, you're going to have negative a plus 45. In order to get this spot here, it's going to be negative a plus 45 times 3. So, or I could say 3 times negative a plus 45. That would give me negative 3a. So let's write that, negative 3a plus 135. So negative 3a plus 135. To figure out what my a value is, I know in this last column, it is going to be 8 plus negative 3a plus 135 is equal to the remainder. It's always this plus this equals that. So that would be 8 plus negative 3a plus 135, and that is equal to 131. That would be the same thing as 8 minus 3a plus 135 is equal to 131. From here, I would have 8 plus 135 is 143, minus 3a is equal to 131. If I make my a positive by bringing it to the right-hand side, I'd have 3a. Bring that 131 to the left-hand side, and you will have 12. Isolate a by dividing by 3, and you are going to have your a value is going to be 4. It's a lot of work. If we were doing a question that required this much work, you would want to make sure by verifying that you did this correctly. How would you verify that? How you'd verify that is if we think that a is 4, we could do a few different things. I could put the 4 here. I could calculate negative 3 times 4. So negative 3 times what I think the a value is, which is 4, plus 135, and I get 123. So this becomes 123. And then 8 plus 123 is our answer of 131. So that's one way that I could verify. The other way that I could verify is essentially, I'll do it on this side here when we're doing the remainder theorem. Okay. So there's an alternate way we could solve this, and that's going to be using the remainder theorem. Students, for this type of question, they always want to default to synthetic division, but I actually find you are going to have more success and make less mistakes if you default to the remainder theorem. So what the remainder theorem, remember, is if you take your given polynomial function and you divide it by the root of the binomial, so that would be 3, the answer is always going to be the remainder. And the remainder, they said, is 131. So I'm going to take this polynomial function, and I'm going to input a 3. And I'm going to calculate what p of 3 is. P of 3 is equal to, take those x's out and input your 3. So that's going to be 2 times 3 to the power of 4 minus 3 to the power of 3 minus a times 3 plus 8. The answer to p to the 3, it's always the remainder. So p to the 3 is 131. That would be equal to 162 minus 27. I'm just going to rewrite this. Negative a times 3 is the same thing as negative 3a, and then plus 8. That would give us 131 is equal to, if I combine my three constants here, I'm going to get 143 minus 3a. Again, I'm going to make a positive by bringing it to the left, and I'm going to subtract 131 from both sides, and I would get 12, divide by 3, and divide by 3. I get the same answer of a is equal to 4. I personally think that you have less of a chance of making a mistake here than you would over on this side. How we would double check if we were doing the remainder theorem is we calculated that a is 4. This was calculated to be 4. If I type in the root of the binomial, so the binomial, remember, the root of the binomial was 3. So if I type in p of 3, and I'm going to now, again, input a 3 every time I see the x, I would have 2 times 3 to the 4 minus 3 to the 3 minus 4, x is 3 plus 8. If you input this on your calculator, p of 3 is going to equal the remainder, and the answer that you will get is 131. So that's what the remainder theorem is. What I would do is I would pause this video, question 1 and question 4. I'm going to set up question 4 with you. And then we will continue with the second part. Question 4, it's actually two different questions in one. So it says, when this polynomial is divided by this binomial, the remainder is negative 14. So that's sort of the first, that is the first question that it's asking. And then it says, what is the remainder when the same polynomial is divided by x minus 2? So that's sort of the second part of the question. But the first part, when this polynomial is divided by x plus 1. So x plus 1 is my divisor. The root of the divisor is negative 1. They are saying that the remainder is going to be negative 14. So instead of doing synthetic division, I want you to do the remainder theorem. So p of negative 1 is going to equal negative 14. So in your polynomial function, when you input a negative 1, the remainder is going to be negative 14. We're going to do that because then we could calculate what a is. So p of negative 1 is equal to. So again, try this using the remainder theorem as opposed to synthetic division. Negative 1 to the power of 4 plus a negative 1 squared minus 16. P of negative 1, so the remainder is negative 14. I would have 1 plus 1a minus 16. And if 1 minus 16 is negative 15, negative 15 isolated, so negative 14 plus 15 would give you 1. So my a value is going to be equal to 1. So I just solved what a is in the polynomial function. So in this polynomial function here, which is identical to this, the a value is 1. What it is now asking is, what is the remainder when it is divided by the divisor of x minus 2. So the root of that divisor is 2. So p of 2 is equal to, they want to know what the remainder is. P of 2 is equal to, take your x's out and input 2. And what you're going to have is the remainder for this is going to be 4. So the a value, the missing a value is 1, and the remainder is going to be 4. Work through class example 1, and then you could unpause it, and we will do the second part. Okay, so for the second part of this lesson, it's going to be on the factor theorem. So just to quickly reiterate what the remainder theorem was, is if you have a divisor and you take the root of the divisor would be a. Into your polynomial function, if you input the root of the divisor, so you input whatever that a value is, the answer is always going to be the remainder. That's the remainder theorem. The answer of the root of the divisor is always the remainder. What is the factor theorem? The factor theorem is as follows, so it's very similar. If you input p of a, and the answer is 0, the remainder is 0. What that means is that if the remainder is equal to 0, then the binomial or the divisor is a factor. So if the remainder is equal to 0, then the divisor, which was x minus a, is a factor. Is a factor of p of x. Why do we want to figure out what the factors are? The factors are the x-intercepts of the graph, and eventually we're going to be graphing this. We need to know all of the x-intercepts. So we want to know the factors of our polynomial. And to do that, we are looking for remainders of 0. Here's class example number 4. Show that this is a factor of this polynomial. So remember, if it is a factor, the root of the divisor is 4. If it is a factor, the remainder must be 0. We could show that using synthetic division and the factor theorem. So if we were using synthetic division, again, upside down division bar, my polynomial I don't need any zeros as placeholders, so let's write down the leading coefficients of each term. So 1, 2, negative 24. The root of my divisor is 4. Carry out the synthetic division, drop that first term, and multiply. Then you're going to add. Then you're going to multiply. Then you're going to add. You will get 0. That is the remainder. If you get 0, so since r is equal to 0, if you get a remainder of 0, what that means is x minus 4, which was the divisor, is a factor of p of x. If it is a factor of the original polynomial, what that means is that this root, which is x is equal to 4, that's an x-intercept. So we are going to have an x-intercept at 4. So the graph, one of the coordinates on the graph would be 4, 0. That's the x-intercept. We could show the same using the factor theorem. So again, this would be the factor theorem. When you input the root of the divisor, if the output is 0, then the divisor is a factor. So here's our polynomial function. We are going to input p of 4. So that would be 4 squared plus 2 times 4 minus 24. P of 4 is equal to 16 plus 8, which is 24. 16 plus 8 minus 24. P of 4 is equal to 0. So explaining this, our remainder is 0. So since P of 4 is equal to 0, the binomial, which is x minus 4, is a factor of P of x. If it's a factor, then the root is an x-intercept, right? And the root was 4. There will be an x-intercept at 4. Class example number 5. Write a binomial factor with integral coefficients, so no fractions, no decimals, of the polynomial p of x if. Okay, so what they're saying for here, p of 3 is equal to 0. What does that mean? It means that we're going to have 0 as a remainder when we input the root of 3. So how we would figure out what the factor is we know that that is x is equal to 3. To figure out what the divisor was, if I bring 3 to the left-hand side, the divisor was x minus 3, right? Because if this is the divisor and I said, what's the root of this divisor? You would say it's 3. So when the divisor is x minus 3, that is going to be a factor of whatever the polynomial was because the remainder was 0. A different one. Let's say I gave you p of negative 5 is equal to 0, and I said what was the binomial or what was the divisor to give you the remainder of 0. In order to get an x of negative 5, the divisor would have been x plus 5. That's the divisor, which is going to be a factor of the polynomial. How you would deal with fractions is the following. We know that this is x. What we could do is we could add 2 over 3 to both sides, but I don't want to do that because it says the binomial factor with integral coefficients, so I can't have fractions. So in this case, what we are going to do is you're going to get rid of that denominator of 3 by dividing both sides by 3. That would give you 3x is equal to negative 2. Then bring your negative 2 over to the left, and you're going to have the divisor, which is 3x plus 2. If you needed another example of a fraction here, you could see if you could figure out if you were given, let's say, p of 4/5, and you're told that that root has a remainder of 0. What was the factor or the divisor that gave you this root? So that is x. Your x value is 4/5. Multiply both sides by 5. 5x is equal to 4. The divisor would have been 5x minus 4. Okay, and then because the remainder was 0, this divisor is a factor of the polynomial. 4/5 is going to be an x-intercept. For class example number 6, you should star this one. Sometimes students, when they see it written in this manner, they get confused or they're unsure sort of how to approach this. What it's saying is p of 5 is equal to p of negative 2 is equal to 0. Essentially, I could split this up. P of 5 is equal to 0. And it's also saying p of negative 2 is equal to 0. What that means is when our root is 5, our remainder is 0. We're going to have an x-intercept at 5. This means that when our root is negative 2, our remainder is 0. We're going to have an x-intercept of negative 2. It says determine a second degree factor of the polynomial p of x. So if I need to rewrite these as the factors. So in order to get x is equal to 5 here, I know that that factor would be x minus 5. And then in order to get a root of negative 2, I know that the factor would be x plus 2. They want to know what the second degree factor would be. So if I take x minus 5 and I multiply it by x plus 2, and I expand this to be x squared, we would have plus 2x minus 5x, which would be minus 3x, minus 10. That would be the second degree. Remember, second degree is a degree of 2. That's the second degree factor of the polynomial. Because if I factored this, I'd go back to x minus 5, x plus 2, and that would give me x-intercepts of 5 and negative 2. Class example number 7. Use the factor theorem to determine which of these two is a factor of this polynomial. So I'm actually going to show you a quick way to do this. Remember that the factor theorem basically states that if you take your polynomial and you input the root of the divisor, so this would be negative 2, whatever your answer is the remainder. So we're going to input p of negative 2, and this one would be p of 1/2. Whatever the output is, that's the remainder. The question is, one of these is a factor and one is not. The one that's going to be the factor will have a remainder of 0, right? The other one, if it's not a factor, will have any number other than 0. So I could take this and I could input negative 2 every time I see an x, and then I could recalculate it and input in 1/2 every time I see an x. The other way you could do this question, and it will be more helpful in later lessons when we're going to be, when I ask you to figure out the remainder of a lot of different roots, is to take this polynomial and just as you see it, input into y1 on your calculator. So take out your calculators, go to y is equal to, and you want to input that polynomial. Here's what the polynomial will look like, which doesn't mean much now, but it will when we graph. I want to know what p of negative 2 is. I could find that in two different ways. I could either look at the table of values, and when x is negative 2, my remainder is negative 90. Or the second way that I could have done this is right from my graph, I could have just done second function trace a value. And when x is equal to negative 2, the output is always going to be the remainder. So when x is negative 2, on the graph, it's way down at negative 90. I'm going to use that function to now find when x is 1/2. So second trace a value. When x is 1/2 or 0.5, that is right here. What is the remainder? The remainder is 0. So the question again was, using the factor theorem, determine which of the following is a factor of this polynomial. The factor is the one with the remainder of 0. So 2x minus 1 is a factor of the polynomial. That means that 1/2 is an x-intercept. This one right here, since p of negative 2 was not equal to 0, right? It gave us a remainder of negative 90. What that means is x plus 2 is not a factor. The last question, which is class example number 8, it's actually the most important question of this lesson. And it's a little unfortunate that there's only one class example because this is what you need to be able to do. All of this is to lead to being able to solve question number 8. Because there's only one of these examples, I am going to do one more homework question that would be similar to this. What question number 8 says is it says that show that 1 is a root of the equation. So we're calling this an equation now because there's an equal sign. Remember that root is the same thing as an x-intercept. So they're saying that 1 is a root, okay? That would be an x-intercept. And remember that if I said, well, what's the factor? The factor to get a root of 1 would be x minus 1. How we would show that it is a root or it is a factor, and they're saying that the remainder would be 0, is we would calculate p of 1. So you're going to input a 1 into all of your x values. So 1 cubed minus 9 times 1 squared plus 20 times 1 minus 12. P of 1 is equal to 1 minus 9 plus 20 minus 12. P of 1 is equal to 0. Since P of 1 is equal to 0, the remainder is 0. What that means is the divisor to get that root, which was x minus 1, that divisor is a factor of p of x, of the polynomial. Then what it says is, it says, what are the other roots? What are the other factors? This is going to be one factor. What are the other ones? So what we've just done is we've just sort of proven that 1 is a factor because it gives us a remainder of 0. How you find the other factors, you are always going to have to use synthetic division. So using synthetic division, again, let's look at our polynomial function. Let's make sure it's in descending order of x and that there's zeros as placeholders, which we don't need. Using your upside down division bar, let's enter the coefficient of each term. So 1 minus 9, 20, and minus 12. We want to input the root of the divisor, which is 1, and then we're going to carry out synthetic division. Drop your 1 and multiply, or drop your first term, and you get 1. When you add, you're going to get negative 8. When you multiply, negative 8 times 1, you get negative 8. When you add, you're going to get 12. When you multiply, you get 12. And then when you add, you're going to get 0. We want the remainder to be 0 because we're told that this is a root. This is a factor, right? So rewrite your polynomial equation as your division statement. So it's always going to be the binomial, which is x minus 1. That's a factor because the remainder was 0. I'm going to multiply that by the quotient. Remember that if this is a third degree polynomial, it is going to be a second degree quotient. We do not need to put plus 0. Okay, so we don't need to do that. I don't need to add a 0. They want me to completely factor this. So we're going to be completely factoring polynomials. We have one of the factors. You could now factor this because it's a quadratic. You learned how to factor quadratics in 10C. What gives you a product of 12 and a sum of negative 8. So P of x is equal to x minus 1. And then if you factor that quadratic, the two numbers that multiply to 12 and sum to negative 8 are negative 2 and negative 6. This would be your answer if the question said completely factor the polynomial. This is in completely factored form. What the question actually was what are the other roots? What are the other x-intercepts of the graph? We knew from this factor that we have an x-intercept of 1. Now I know that I've got an x-intercept of 2 and an x-intercept of 6. So the other roots are 2 and 6, because they already told us that 1 was a root. But there's 3 x-intercepts of this graph. Here are your homework questions. So you could pause that, get that circled. Question number 11, just you might want to note, is a factoring by decomposition. I will work through on this video now question number 10, because again, that's going to be the most similar to this last class example, where if you were to be tested on anything in this lesson, it is going to be, can you do question number 10? So if you want to do question number 10, you could follow along. Question number 10 is actually complex in the sense that we're going to be completely factoring like we did in that last class example. However, before we do that, we have to find this missing value of k. So how we're going to find that missing value of k is they tell me that when I input a -2, the remainder is 0. Okay, so again, that's telling me actually a couple things. Because the remainder is 0, I know that x plus 2 is a factor. That's going to be one of the factors. It wants me to find the other 2 factors. Before, though, I could do that, I need to figure out what k is. So let's figure out p of -2. -2 cubed plus k times -2 squared minus, in a bracket, -2 minus 2. P of -2 will give me the remainder. The remainder is 0. That is equal to -8. I'm going to rewrite this as 4k. This becomes +2 and then -2. That will cancel. I'm going to bring the 8 to the left-hand side and dividing by 4. I know that k is equal to 2. So going back here, I know that this missing k value is 2. Again, to double check this, if you now input -2 into this polynomial function and hit enter, your remainder will be 0. It wants us to find the other factors. We must use synthetic division to find the other factors. So according to my polynomial function, I don't need any zeros as placeholders. I'm just going to now input my coefficients. 1, 2, -1, -2. I know that -2, when the root is -2, the remainder is 0. So let's show that. Drop the first term and multiply. Add and you get 0. Multiply and you get -2. Add and you get nope, sorry, 0 times -2, 0. -1 plus 0 is -1. Multiply and you get 2. Add -2 plus 2 gives us what we were looking for, which is a remainder of 0. This is our q of x. Rewriting the polynomial function, it is going to be the divisor, which was x plus 2, times the quotient. And the quotient, remember that this is a third degree polynomial, so therefore the quotient would be a second degree. So that is a 1x squared. I don't need to write plus 0x, so it's just 1x squared minus 1. It said completely factor. You will always be able to factor this, and it's always going to be either an inspection, decomposition, or difference of squares question. This is a difference of squares. Two terms separated by a minus. Both terms can be square rooted. P of x is equal to, the first factor is x plus 2. The second two factors, using decomposition, will be x plus 1 and x minus 1. So the question says, the complete factoring of p of x, this is what I would box in. They want the factored form. The question could also include what are the roots, or what are the x-intercepts, or what are the zeros of the polynomial function. The x-intercepts or the roots would be -2, -1, and 1.